So now we have two sets, we are all familiar. So when you have a light, when you have an interface, you can always define whether the electric field is perpendicular to the interface or the magnetic field is perpendicular to the interface. And these are the two situations that we see. Fine. So we have to solve them separately. So we start with the TM mode. So for the TM mode, let's write down the relations that we have. We have Ez is equal to minus kx epsilon naught omega h y. Okay, this comes from sorry, this comes from the sixth relation. We also have Ex. These are the expressions for Ex. Ex is minus I by omega epsilon naught del h y del z. Okay, and h has only the y component, right? It doesn't have anything, and this we get from the fourth relation. Okay, so these are the electric fields in terms of hy. Now in this case, as we know, hy is only y, so the whole magnetic field is along the y direction. Here h is along the y cap only, so we can actually express the h field in a way that we want to express. Okay, so what do? We have to, of course, express in the two different regions. Let me get back to the black. So we have for z greater than 0, that is, we are sitting in the dielectric. In this case, let's define the h. H will have the standard form that we have thought of. So we have AD, which is some constant, let's say some amplitude, and we have the propagation along x, and we have the other term, which is basically the evanescent term, which is minus k dz. Okay, the temporal part is not here because we are only considering the spatial part. The temporal part, if you add it to it, it will be exponential minus I omega t. So right now we are only dealing with the spatial part, and if you now plug this in to these two relations, so we will plug it in here and plug it in here, and we will get the expressions for Ez. So what we get is Ez will be, it had all these minus kx by epsilon naught omega, and hy, which is nothing but ad exponential I kxx minus kdz. And for Ex we have minus I omega epsilon naught, and a derivative of h with respect to z, which gives you another minus kd, and the rest is the same. Fine. So we'll end up with these three relations for z equal, say z greater than 0, and we will also have a similar thing for z less than 0, right? And there what we will have, the hy will be slightly different, which is, so please note again, I'm missing out. So here it will be epsilon d because we are in the dielectric. Now in the conductor it is AC exponential, it's the same I kxx because it's the propagation, same propagation. This one becomes rather kcz, z being negative. Now then we have Ez is minus kx epsilon c epsilon naught omega AC exponential x kc z. And we also have then the expression for Ex, which is again minus I omega epsilon c epsilon naught kc AC exponential I kxx exponential kc z. Okay, so these are the 6 relations we get. We get the fields for less than z less than 0 and z greater than 0. So the next thing, of course, the standard way of solving is finding the boundary conditions, and then we can solve for AC and AD and whatever relations we can get. So what are the boundary conditions that we need to consider in this situation is basically that your parallel component Ex is continuous at the interface. Interface means z equal to 0. And the other thing we will consider is the magnetic field Hy is also continuous at the interface. This is primarily because there is no free current in the interface. So if that is the case, what we will find is if we equate, let me just have another color. So if we equate this relation with this relation at z equal to 0, so the exponential kdz minus kdz vanishes, it becomes 1. Then you will find that from this boundary condition, you get AD is equal to AC. That is one relation we get. And for the other boundary condition, what you will get, so we have to put at z equal to 0 and we equate the two x terms. So this one is equated with this relation. If we do that, then as you see that what you'll see is KD, and putting in that AC is equal to AD, what you have is KD by epsilon D becomes equal to minus KC by epsilon C. These are the two relations we get from the boundary condition. So actually this is quite interesting. That tells you how the extent of the evanescent waves within the two media. So KD by KC is minus epsilon D by epsilon C. So you see what will be the extent of the evanescent waves within these two medium. Fine. So we will carry on today because this will lead to the completion of the TM mode. So we have nearly got the relations here, but again we have KD, KC in our equation. So somewhere we have to replace them because we want the dispersion relation of Kx in terms of epsilon C and epsilon D. So in that case, what we'll do is we'll make use of these early equations that we have got. Like these relations that we had got, this is what we will make use of. So we have a relation between Kx and Kd, and here now we have a relation between Kx and the epsilons, Kd and the epsilon. So we will have to just use those relations to replace them. So what we had in the previous relation, I'll use the black ink. So what we had was, Kc square plus K0 square epsilon C minus Kx square is 0, and the other one was Kd square plus K0 square epsilon D minus Kx square is 0. So if in these two relations, if we take the two terms on the right to the right hand side, and we find a ratio of Kc square by Kd square, what you'll find is it is nothing but K0 square epsilon C minus kx square by k0 square epsilon d minus kx square. Okay, and this relation but we know that this left hand side is nothing but epsilon d square by epsilon c square from this relation. So once we have this, you have to do a little arithmetic and you will land up to the equation that we need. We eliminate, so we have eliminated all epsilon, kc and kd, so we have a relation of kx. So kx is nothing but k0 square root of epsilon 1, epsilon 2 by epsilon 1 plus epsilon 2. So this will lead to the dispersion relation, because we know knowing the form of epsilon 1 and epsilon 2 in terms of omega, if you plug it in, this gives your dispersion relation, dispersion relation. Okay, so this is where we stop today and we will continue next day. Thank you.